Hello and welcome to this video. We are going to discuss linear relationship between matrix columns. And why is this question interesting? Assume we have some set of vectors. Here are the vectors in R3, but they can be from any other space. And then there can be different questions. For example, which subset of these vectors are linearly independent? Or which of these vectors can be expressed as linear combination of the others and how? These can be very relevant questions. And now that we know so much about matrices, we have a plan. We can write all these vectors as columns of a matrix. And then we can study what are the linearly independent columns of this matrix and how the columns can be expressed through each other. And how we're going to do it? Again, we will use elementary row operations and echelon form. I will show you the results and the example on the next slide. Here is again my matrix, and using elementary row operations, I have transformed it to this row-reduced echelon form. And now there is definitely a relationship between how columns of B are related to each other and the columns of A are related to each other. And this result is established in this theorem 3.16. The theorem is as follows. It says we have a matrix M by N, so we have N columns, and also we know that the rank of A is R. And also we know that B is a reduced row echelon form of A. We will denote A1, A2, AN to be columns of A, and B1, B2, Bn to be the columns of B. Then the statement of the theorem consists of several parts, and we are going to discuss them one by one. We start with part A, and it says that B has exactly R non-zero rows where R is rank of the matrix A. We are not going to prove this, but we are going to look at this example. In the reduced echelon form, every non-zero row has a pivot. Moreover, the columns of pivots contain all the other elements 0. That makes these rows linearly independent. In other words, in the matrix B, the number of non-zero rows exactly equals to the number of linearly independent rows, and that is equal to the rank of B. But because we used elementary row operations, the rank of B is equal to the rank of A. And that's how we can interpret the statement A. I have skipped the statement B of the theorem, and now let us look at statements C and D. And for that, I am going to offer you one observation. The observation is that when we perform row operations, we apply them to the entire row. So to all the elements of all columns that belong to this row. And therefore, these elementary row operations do not change linear relations between columns. For example, when B1 and B2 are linearly independent, as here, then A1 and A2 also will be linearly independent. And it is easy to check that if B3 is B1 minus B2, that is obvious here. Less obvious, but it's easy to check that A3 is also A1 minus A2. You may ask, is that a proof? Well, if you argue very well, it can be, but we also can prove this formally, and we are going to do this on the next slide. The proof is, of course, based on the fact that elementary row operations are equivalent to matrix multiplication, and this is what we are going to use. Each column of matrix B is nothing else but the column of matrix A multiplied from the left by the matrix, which is a product of elementary matrices, and this matrix M is invertible. When we multiply both sides of this equation by M inverse, then we obtain that the columns of A are in fact also columns of B multiplied from the left by some invertible matrix. Now, if B1, B2 are linearly independent, then multiplication with invertible matrix will not change that, and A1 and A2 also will be linearly independent. So how do we find linearly independent columns? First, find linearly independent columns of B. Of course, this will be simply pivot columns. And then linearly independent columns of A will be on the same positions as pivot columns of the matrix B. It is also very easy to establish other linear relations. For example, look at the fourth column of matrix B and write it as a linear combination of the first and the second column. Write it down yourself and then we'll discuss it together. It is easy to see that pivot columns are columns of a standard basis, and then this vector is very easy to write. It will be minus 2 times the first column plus 3 times the second column. Now look at the matrix A. Look at its last column, and it will be very easy to check that this last column also satisfies the same linear relation. In fact, when I make exam problems, I make it in the following way. I first write down the matrix in the reduced echelon form. I look at its pivot columns. I come up with 2 arbitrary columns as pivot columns, and then I make other columns as linear combinations. So my question to you is, please write down the third column as a linear combination. If you look well, you already see that actually I had it in the example. The third column of B is B1 minus B2, and then the third column of A is also A1 minus A2. And this is how you can construct the entire matrix by knowing only its reduced echelon form and its pivot columns. I hope now you understand how the linear relations between the columns of a matrix are connected to the linear relations between the columns of its reduced echelon form. Thank you very much for your attention.